Welcome to General Chemistry Mini Lecture Series, Lecture 40, Chemical Bonding Models. The driving force for formation of compounds is to attain a stable electron configuration for each element in the compound. Except helium, all other noble gas elements have 8 valence electrons. Therefore, noble gases possess the most stable electron configuration. The octet rule is very important in chemical bonding. During chemical reactions, atoms either exchange or share electrons to attain an electron configuration with 8 valence electrons, octet, to have noble gas electron configuration NS2 NP6. 2 plus 6 equals 8 octet. However, there are exceptions to the octet rule. First, expanded octets. For elements in period 3 and beyond with empty d orbitals, they can have more than 8 electrons surrounding them. On the other hand, there are incomplete octets for the smaller, lighter elements. And those elements, after forming compounds, typically will have helium-like electron configuration 1s2. Because there are 2 electrons for helium, therefore its electron configuration is just 1s2. Hydrogen either shares electrons or gains 1 electron to have an electron configuration of 1s2. Although it commonly loses 1 electron to become hydrogen plus, which means there's no valence electron here. Therefore, there's no electron configuration for hydrogen ion. Lithium, there are 3 electrons, loses its valence electron, then it becomes a lithium plus. Beryllium can lose its 2 valence electrons to form Be2 plus ion with electron configuration of 1s2. However, beryllium normally shares its 2 valence electrons in covalent compounds that will result in 4 valence electrons surrounding beryllium. When boron loses its 3 valence electrons, the resulting ion will have 1s2 electron configuration. Although boron commonly shares its 3 valence electrons in covalent bonds, in that case, there are 6 valence electrons surrounding it. There are odd number electron species. Obviously, they will never meet the octet rule because they have odd number electrons. For example, nitrogen monoxide has 1 unpaired electron. The odd number electron species, they are called free radicals, and they are very reactive. It means that they are not stable. There are mainly 3 types of chemical bonds. Ionic bonds are formed by transferring of electrons. Covalent bond for nonmetals to nonmetals. Covalent bond is formed by sharing of electrons. The third one, metallic bond. That's for metal to metal, and it's caused by electron pooling. Let's take a look at those examples here. First, for ionic compounds. Let's take sodium chloride as one example. So sodium chloride crystal, it is formed by sodium cation, the purple ones, and chloride anion, the green ones. Sodium metal loses one electron, becomes sodium ion. Where does that electron go? Chlorine receives that electron, becomes chloride. That's why we have sodium plus and Cl minus. Then the attraction between the two forms ionic bonds. Now let's take a look at the electron configuration or the stability of the system. Sodium plus has neon's electron configuration, 8 electrons surrounding it. Octet rule. It meets the octet rule. Chloride has argon electron configuration, also 8 valence electrons surrounding it. That also meets the octet rule. Sulfur dioxide contains covalent bonds that are formed by sharing of electrons. For example, between the first oxygen atom and sulfur, 4 electrons are shared by the two elements, and then a double bond is formed. A double bond, that's a covalent bond. Now if you focus on the sulfur atom and the last oxygen atom, both share one pair of electrons, and that form the single bond. Now if you look at the number of electrons surrounding each atom, oxygen, the first oxygen, there are 8 valence electrons. Sulfur, there are also 8 valence electrons. And the last oxygen, also 8. So therefore, octet rule is met here. Now let's take a look at the sodium metal. The metallic bonding occurs between those sodium cation ions, the purple ones, and the electron C. Therefore, metallic bonds are formed by electron pooling. The contents of this slide were already covered in lecture 11, so you can take some time to review the properties of molecular and ionic compounds. Now let's pay attention to this property of ionic compound. Ionic compounds are brittle. Then you may ask, why ionic compounds are brittle? The attractive forces in ionic compounds hold ions in specific positions. As you can see here, the cations are in purple and the anions are in green. The arrangement of those cation and anions is very specific. Because of that, moving the ions out of position requires overcoming those electrostatic forces. That's why the sample resists denting and bending, as well as why they are brittle. If we apply external forces to ionic crystals, what happens? See those first two columns, they move down. But now let's take a look at those ions. Here, the arrangement of ions in this picture maximizes the attraction between cations and anions. That's why you see each anion is surrounded by several cations, and each cation is surrounded by several anions. That way, the electrostatic forces is maximized. But look at this picture now. Because of the application of external forces, now look at the arrangement of those ions. Positive, positive, negative, negative, next to each other, positive, positive. Do cations like each other? No. Do anions like each other? No. If they don't like each other, they repel each other. As a result of that repulsion, cracks occur. That's why ionic compounds are brittle. Metals have low ionization energy, and that allows them to lose electrons very easily. The lost electrons form a sea of valence electrons. All of those electrons in the sea are shared by all other atoms and metal ions. If we take a closer look at this picture, we can see the purple metal cation ions and the greenish electron sea. The valence electrons, they are delocalized throughout the metal structure. They are not localized electrons anymore. The metallic bonding is resulted by the attraction between the cation ion islands and the electron sea. That's the mechanism for metallic bonding. Because electrons in metallic crystals are mobile, they flow inside metallic crystals. That's why metals conduct electricity. However, heat causes metal ions to vibrate faster, making it harder for the electrons to make their way through the crystals. That is why when temperature increases, conductivity decreases. When heat is applied, metals are malleable. When external forces are applied, the heated metals just simply deformed or reshape. They don't break like ionic solids. That is because the metallic bonding is the attraction between those cation ion islands and the electron sea. There are no cracks. This is actually why blacksmiths can make knives, swords, horseshoes out of metal blocks. That's it for Lecture 40. If this video is helpful, please subscribe and recommend this channel to other people who are also interested in learning chemistry. I will see you guys in Lecture 41, Lewis bonding theory.